Все, запись пошла.
Yeah, so maybe we should try to solve some problems today, yeah? So for instance, well, just to make sure that you know some what to do with some basic questions like so for instance suppose we deal with what with rational number m or even an integer yeah, depends what you want. So maybe and suppose that well, don't want it to be 0, for instance. Well, say let it be negative. So and the question is do there exist a cyclic extension of Q of degree say 4 containing square root of m. Sorry, does they exist? So, or do there exist cyclic extensions of the rationals of degree 4 containing square root of m? So what could you say on this?
Cyclic means that its group, its Galois group is cyclic.
Yes, it means, first of all, it means that it is cyclic means that it is Galois, and its Galois group is cyclic, and so its Galois group is isomorphic to Z mod 4. Yeah, so for instance, let cyclic, maybe we should denote this by K. So we have K, and we have Q. This is cyclic of order 4.
So
yeah.
maybe then we can add to Q I and square root of minus m. So the square root of minus m gives us an extension of degree 2, and I, the square root of minus 1, gives us also an extension of degree 2.
Okay, so you propose.
So I think it's yeah, it's Q of square root of minus 1 and of square root of minus m, but there's a chance that this extension's Galois group is isomorphic to Z2 times Z2.
Z mod 2, yeah. And the moreover minus m may be a square. So it may happen that this is already a rational number.
Then we is there any okay, then we in case minus m is is a square rational number. Okay, then there are two cases.
Yeah.
The first case is the easiest one, where minus m is a square in Q.
But anyway, you see that the problem is that even so, if minus m is a square, then you get just
Then we add the fourth root of unity. So of degree
but
the root
this
of
is
unity of degree 4.
fourth root of unity.
Okay. Of degree, then the root of degree 8.
What does this happen? Does this help?
Uh,
So what is the Galois group of
Q Z M? It's Z mod M invertibles.
yeah. So for instance, when m is equal to 8, this gives you z mod 8. And what is this?
It's
You see that?
Z mod 4.
No, it's not z mod 4 because any, you know that any square, the square of any odd number is so m. If n is odd,
Well,
is
if n is
then then its square is congruent to 1 modulo 8. You see?
uh,
So
yeah.
this is z mod 2 what? Z mod 2 square.
Mm-hmm. And it's not Z mod 4.
Mm-hmm. But well, you see that what we definitely know. Do you know how can we construct an extension of degree? Or how to construct a cyclic extension, at least in some cases?
Well,
Ah,
find some group that um, the invertibles of which find some m that then take z mod m invertibles and then look at the way this can be disassembled as a product. So
uh,
basically we find some m, then we look at z mod m, and we look at the groups. Those are at the set of groups that the product of which gives us z mod 8, z mod m invertibles. Then we choose a subgroup of the order we need.
well, I cannot say that I understand what you're saying, but
Можно на русском просто скажу быстро?
да-да.
Смотрите, мы что делаем? Мы берем, раскладываем, берем z по модулю m, раскладываем в произведение.
А почему Z по модулям? Причем здесь
Э, Ну, потому что технически мы так можем найти любой простой... Ну, во-первых, у нас любой простой минус один может быть.
нет. Wait, you see that the problem. So once again, the
So,
problem is that to find a cyclic extension of the rationals containing square root of m. Yeah, this
мгм,
means that we want to have a tower of extensions like this.
мгм.
Okay, so uh, what can you say about these two extensions?
Well, first of all, Q of the square root of m can be q square root of minus 1 can be equal to q square root minus 1 in case m is a square. And it
But
can
why do you
be
care? Why do you distinguish some cases? This is
uh,
just this is just an extension of degree two, yeah.
um, yeah,
And what can you say about this extension? Assuming that
k over q square root of m,
yeah,
its degree must be 2.
yeah. So both of them are degree two extensions. And do you know how do degree two extensions look like?
Mm, it's a square root of
Of
something
something? Yeah,
added to the field.
yeah. So this means that k is equal to is just you see that it means that it is what is this? This is just a. So what are the elements here? Elements here are just linear
A plus
combinations.
b square roots of m.
Yeah, where a and b are rational numbers. Yeah, so this means that uh, this extension is just obtained by adding square root of this element.
Mm-hmm.
In principle, you see that, so we can denote this by alpha. You see that in principle, we need not to add square root of m if b is, so if b is not 0, then square root of m is just alpha square minus a over b. Yeah, so we need not to add this element. Yeah, but of course, if if b is 0, then k is square root of a, and it's generated by square root of a and square root of m. Okay, but the point is that actually this would mean that
A and b are still rationals.
yes, yes. For for some a and b in Q. Okay. Yeah. So, but first of all, the point is that here the group is so the what is the Galois group of this field? Yeah, of square root of a square root of m. Uh, well, maybe it depends a little bit on a and m. Well, I mean,
It's Galois group of this extension over q.
yeah,
Mhm.
but you can just consider all automorphisms, yeah, because all automorphisms are identical on the rationals. Yeah, so the point is that actually, what can you say? You can say that well, of course, we know that a is not 0, yeah, and moreover, a is not a square. And actually, this field is generated by by what? Can you show that this is actually the same as, for instance, this field? Can you show this?
Let's take the square of this element.
Oh, yeah. So this is beta.
Yeah, beta. Then
Yeah. So beta square is what is beta square? It is a plus m a plus m plus twice.
Square root of am.
Okay.
Um, then we can.
Oh, I'm sorry.
Mm,
Yes. Yeah, and then.
mm, so we want square root of a and square root of m to be in this field. So for this
Mm-hmm.
we need square root of a minus square root of m.
But do we have it?
We have it square. To
Yeah.
a plus m twice minus beta square is uh, the square of square root of a minus square root of m.
Okay, so twice a plus m minus
Beta,
beta square.
yeah, beta
Minus
square
beta or beta
minus
square?
beta square.
Mm-hmm. Okay, it is square
Ah,
root
no,
of
no, no, no,
2.
no, no need for this. We have minus m, then a minus m over beta is square root of a minus square root of m.
Yeah, and we probably don't need
Yeah, we don't need this.
yeah, so yeah, so square root of a minus square root of m is a minus m over beta. Okay, and yes, and then we get
Hmm.
get a
Square root of a and square root of m are in this field.
yeah. Okay, all right. So uh, yes, so for instance, yeah, and what is the minimal polynomial of beta?
It's x minus uh,
X
yeah,
minus.
x square minus a minus m. It seems minus a minus m. No, my a minus m are in brackets, and x square is out of these brackets, outside of these brackets. So it's x square minus a minus m.
Like this?
Nope. A minus m isn't must be in brackets. Yeah,
Like this?
like this.
Um,
Or
well, I don't understand this. You see that actually we
oh
have
yeah, yeah. You see here. No, nope, nope.
you see we just have started to calculate beta square. So it was a plus m plus twice square root of a square root of m. Yeah.
Mm-hmm.
So
And
what is this? So when you subtract a plus m from beta square,
mhm.
what do you get?
Two square roots of a m. Oh,
Yeah.
then minus x square. Mm, okay, here we open the bracket.
Now you see what happens if you move this sum to the left, to the left
Mm-hmm.
hand side, and square both of them.
Minus 4 am.
minus 4am. Yeah. So it is actually yeah. So this is a polynomial of degree 4. So that's exactly what we need. Yeah.
Mm-hmm.
And so this is the minimal polynomial, and the question is, what is the Galois group of this extension?
It, it's it feels like it must be well, it seems that it must be z2 times z2.
Yeah, that's
Because
right. Because
bec-
yeah,
bec-
because we see that
because we added square root of a and square root of m.
yeah, yeah. So they are in the case when they are independent. Well, for instance, they are in particular they're not equal. Yeah,
Hmm.
if they
And
yeah
well, they must be independent in cases they're not equal, and perhaps in cases where their signs are different.
no, it doesn't matter. I mean, they just they should be uh, distinct. Uh, they should be distinct non-zero elements in the quotient of the multiplicative group by the squares. So
Mm-hmm.
so A is not equal to B in this quotient, and that's
To m maybe.
sorry, yes, to M. Yeah, M, and of course both of them should be non-zero. Well, non-zero, I mean non-one, so minus one. Okay. All right. Yeah. So this is so this case doesn't give a degree or a cyclic extension. Yeah. So maybe this one could work. So what about this one? So this is maybe a 2 star and 2 star and 1 asterisk. Yeah. So what happens? So what is the minimal polynomial of alpha? Well, we just square this. Yeah, it's x squared minus a. So you get rid of this square root. You subtract a. Then you can square again, and you will get b square m. Yeah. So this b square m. Yeah. So this is the minimal polynomial. Of course, this is of degree 4. But what are the roots of this polynomial? So if the roots are there are alpha, minus alpha, and well, alpha prime, which is something like square root of a minus instead of plus, and minus alpha prime. Yeah. So the question is what is the Galois group of this extension or of this polynomial? You see, you have we have two pairs. Yeah. So what can happen with this? For instance, we cannot if so this is alpha, this is minus alpha, alpha prime minus alpha prime. So you see that mm, we have two pairs where
Well, the first thing we want to say is that there is an element of order 2. It's minus 1, so which swaps alpha and minus alpha and alpha prime with minus alpha prime.
yeah, you mean this one, yeah?
Yeah.
Okay, and what else?
Then there also must be an element that swaps alpha and alpha prime, and then it must swap alpha prime and minus alpha. No, it must swap minus alpha and minus alpha prime. It swaps the columns like this.
Yeah, so you see that the point is that the point is that so the question is whether do we have a cyclic permutation? So of
Uh,
course,
it doesn't.
sorry, not cyclic, the cyclic permutation permuting all the roots.
Mm,
You see, if alpha
if
goes
alpha goes to minus alpha, then alpha prime goes to minus alpha prime. And if alpha goes to alpha prime, then minus alpha goes to minus alpha prime. Then the only way left is to switch alpha and minus alpha prime. Um, what happens if we map alpha to minus alpha prime?
you see, there is no difference between alpha prime and alpha.
Okay, all right, then minus alpha will swap with alpha prime. So we have three elements of order two. So basically, it's z2 squared again.
Yeah. So once again, so first of all, if alpha goes to minus alpha, then we have no choice that these two also interchange between them.
So
Yeah. Wait,
we swap rows,
yeah.
columns,
So if
or diagonals.
yeah, so first, yeah, maybe we should write this more explicitly. If alpha goes to minus alpha, then minus alpha
Then alpha
goes
prime
to
goes
alpha,
to.
and that's it.
Mhm.
That's it. This means that we have already one transvection, yeah. So which is which means that it's not a cyclic permutation of these four elements. Yeah, so it doesn't work. So not does not generate Z4. Does not generate Z mod 4. And next, and similarly for yeah maybe 4. Okay, so next, if alpha goes to alpha prime or alpha minus alpha prime doesn't matter. Then what can we say about then of course minus alpha goes to minus alpha prime. Um, and where does alpha prime go?
Mm, then alpha prime should go to alpha.
Why alpha
Uh,
prime?
okay, then it if it goes to minus alpha,
Yeah, first of all, you see, so alpha, yeah, must go to what? To either alpha
alpha or
minus.
minus alpha.
Okay.
If it goes
So if
to minus alpha, then
so if it goes to alpha, then it is bad. It is not yeah not a generator, not a generator of Z mod 4. Okay, so if it goes to minus alpha,
then it's then the square of this map is alpha prime goes to minus alpha prime.
then sigma square maps uh, alpha to minus alpha. Wait,
To
goes
minus alpha.
okay.
No, it maps alpha prime to minus alpha prime, and alpha to minus alpha. Yeah.
Yeah, and so alpha prime goes to minus alpha prime, yes. And what's wrong with this?
Nothing's wrong. Nothing's. Well, we do have this map here.
Yeah, and actually,
And wait, why did we decide that if alpha goes to minus alpha, then minus alpha goes to alpha?
hmm,
And also we got one more vote for double Friday, double Wednesday seminar.
sorry.
У нас еще плюс один человек, которому было бы удобно по средам.
Ну отлично.
Вот.
Это в смысле Юния?
Это Влад.
Влад,
Влад
хорошо.
добавился. Ну, в
Замечательно.
таблицу он не отметил, но в
Он сказал,
чатике, в
да?
чатике курса он написал,
А,
значит, цитирую,
ну хорошо.
было бы хорошо. Вот про среду.
Хорошо, замечательно. Так и сделаем. Okay. So, yeah. So yeah. So alpha prime. Yeah. So what's wrong here? Nothing.
Here nothing's wrong because then minus alpha. Wait, just minus alpha goes to minus alpha prime, and everything's fine.
Yeah. Okay. So now yeah. So yeah. Uh, Maybe the only problem is that mhm. Okay, let's
Okay,
see. So
let's take a look at sigma cube. Then, so we see that we can see that sigma maps alpha to alpha prime, um, alpha prime to minus alpha, then minus alpha to minus alpha prime, and minus alpha prime to alpha.
mhm. Oh,
Then sigma
okay.
squared gives us alpha to minus alpha, minus alpha to alpha. Well, it just swaps the sign.
Okay, but maybe oh, by the way, can you calculate a discriminant of this polynomial?
Mm,
So see, we have four. So discriminant of this
is
polynomial
the product of all is the product of squares of
of difference of all differences.
of all differences.
Yeah. So for instance, yeah. So here the first difference, this one between first two is 2 alpha.
Mm-hmm.
Next alpha minus alpha prime. Then alpha plus alpha prime.
Mm-hmm. Then
Next,
two alpha prime.
yeah. So this we considered we have considered all differences with this element.
Mm-hmm.
Next, we consider difference.
Then we have alpha prime plus alpha.
Yeah, alpha
Prime
plus
plus
alpha.
alpha, then 2 alpha prime, and then
Uh, wait, 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 wait. So
so first
this minus this one, and yeah, and minus alpha plus alpha prime. Yeah, so this is
mm-hmm,
plus. Uh, and next, so we have counted this and times twice alpha. Yeah,
mm-hmm,
twice alpha prime. and
Yeah.
all this square, yeah.
Mm-hmm.
Okay, so is that correct?
Yeah, it's four. No, it's 16. Alpha square, alpha prime square. Um,
So
by
yeah, yeah. So
alpha
this is
minus alpha square minus alpha prime square. Uh, for the fourth degree of, yeah,
okay.
all of this.
Okay, and then so what can yeah? So what is this? This is hmm, so what is this? Alpha square is a where is it? Where is it?
Alpha square is a plus
Yeah,
b square roots of m.
yeah. So it is uh, uh,
It is 16
y.
a square minus b square m, because alpha prime squared, uh, and well,
Yeah, something like this.
b square. So the discriminant is 16 a square minus b square m, and yeah, this is the square root of a minus a square minus b square m. Yeah.
Mm-hmm. Okay, so this doesn't give much, yeah? So this is just
Well, this gives us a lot because we get 32 a square minus b square m, b square
yeah, it doesn't yeah
uh,
because
b fourth the fourth power of b m square,
mm-hmm,
and it seems to be, well, the only case that prevents us from being well, this is zero only when b is zero, or
mm-hmm.
a square equals b square m, and this cannot
Yeah,
happen.
yes, of course, this is not very useful. Yeah, just
This thing. So the thing is, the discriminant is never zero,
mm-hmm,
because it can be zero because of three reasons. The first is b equals zero, and we are in the case where it does not equal zero,
mm-hmm,
because it's one asterisk.
mm-hmm.
Then when m can equal zero, and uh, it's impossible.
Yeah, yeah, but actually, you see,
And the, the 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 last case is when a square equals b square m, and it's also impossible because a and b are rationals, and m so then their squares are both more than zero, and m is less than zero, then b square m is less than zero, then a square minus b square m is always bigger than zero in
mm-hmm,
cases where none of these numbers are, well, in cases when there are no zeros among these numbers.
mm-hmm. Okay,
Well, no, in cases where when b is not zero also.
mhm.
So this thing is always greater than zero, because uh, it's a
Yeah.
square of non-zero number.
Oh, I would say of a real number.
Of a, uh, Yeah. Oh well. Um. So yeah, in the end, it's a square of some real number. Oh well, of some rational number actually.
Well, this is not a rational number because
No, 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 no.
because
Okay. This square is a rational number.
this one,
No, no. The square of
the whole,
this whole thing is a rational number.
yes, yes, the whole is rational.
So this whole is rational, and also it's non-zero, and it consists of squares and one
Yeah,
non,
yes.
non,
Even
non
it is positive.
yeah, it's always positive the ah, because a square minus b square m is always positive,
Mm-hmm.
and the others are, well, it's b the fourth power of b and m square, well, they are also positive.
Okay. Yeah. All right. But then, yeah. So the question is mm, whether there exists such yeah. So, but in principle, why not? Why should not this exist? Why? I think that's not a problem. Yeah. So you just because you see that the group is transitive. The group is transitive. So mm, so there is I mean the Galois group is transitive. So there is such an element. So what maybe I'm sorry, this one, yeah. So this, yeah, we should separate these cases. Yeah. So the point is that mm, no. I'm sorry. We do not separate this because yeah. So this one because yeah because we have fixed this, yeah, and therefore we separate this case from this one, yeah. So actually you see that our group is transitive, so there is such a so there exists um, such sigma because our group is transitive, yeah. Sorry. Yes, it's not true. It's not true because we have fixed. Yes, because we have. Sorry, it's not true because we cannot. We have already fixed its value of this
Well,
automorphism
we already
in
fixed
alpha.
sigma by appointing the images of alpha and alpha prime.
Uh, yes, well, not really fixed because so far we don't know whether it is determined by this condition. So um, maybe there are several sigmas with satisfying mapping alpha to alpha prime. Yeah, so that's the question. So, but let's see. Let's see. So maybe we should try to look at. So you see that we want to know. All, so what is the Galois group? It is the group of those permutation that preserve on all relations. Yeah, between the roots. So um, this means that so if alpha, so we know what. Yeah. So can we relate alpha and alpha prime, for instance? What is alpha? Yeah. So what is
So
alpha?
alpha prime
Alpha.
is a minus. Oh
Yeah.
no,
It's here. Alpha
yeah.
prime is here.
Alpha prime
Yeah.
it's
Alpha.
square root of a square minus b. Well, yeah. Okay, alpha
Yeah.
square plus alpha prime square equals 2a. Yeah.
Okay. Yeah, but of course this gives us more or less nothing. Yeah, because because we're interested in the sign of yes, we're interested
what?
in this
The
of
sign.
you see that we care about you see that there is a big difference between alpha and minus alpha
Yeah.
as the yeah, so that's yeah, we can so maybe we should think of this somehow yeah, maybe we should think of alpha plus alpha prime or alpha minus alpha prime. So what can we say about this element? Can or if we can say something. So for instance, this you see that this element goes we don't know where does it go. Um,
Well, it must go to sigma of alpha plus sigma of alpha prime, and it will be uh, minus alpha prime plus minus alpha.
yeah. Yeah, but the problem is that we don't know the image of alpha prime. Yeah, that's the
So
problem.
let's assume that the image of alpha prime is minus alpha. So actually, oh, well, there is a possibility that such sigma exists, and so
Yeah. So
do I
if
understand?
exist,
Do
yeah.
I understand correctly that there is a probability that such element exists, and we want to prove that it exists in any case?
Well, I'm not sure. So it's just it's a question. So yeah, you see that this goes to so assuming that it exists. This goes alpha goes to alpha prime and alpha prime goes to minus alpha. Yeah, and this goes to what to alpha prime plus alpha.
And
So
oh well, yeah.
okay, so. Mhm. Okay, so then the question of whether this is possible, yeah. Uh-huh. Or another, yeah. So that's the question, and so that our can this happen that can it happen that this these elements are permuted cyclically, yeah. So what? Yeah. So the option is that they are permuted this way. So like this is one element and this is another element. Yeah. Or yeah. So this is yeah. This is one. This is and the composition is yeah. And so the composition is like this. Yeah. And also identical permutation. So they are you see they are pairs. So they are pairs, and the point is that these yeah, actually, you see that. So what is this group? So this is Azimuth 2. It is isomorphic to Azimuth 2 square, but you see that the point is that this is these are even permutations. Yeah, so these are even permutations. Even permutations. Yes, Do you agree that all these permutations are even? That we considered before, in case, for instance, in case, yeah. So in these cases, yeah, like yeah, these ones. Do you agree that all these permutations are even? So they are like 1, 2, 3, 4, and 1, 3, 2, 4, and so on. Yeah. Okay. Do you agree?
So
Well,
these are 1, 2, 3. Okay.
yes, they are even because you see that they are products of they are products of pairs of transactions. Yeah. Some of this. Do you agree that they are even?
Yeah.
So
And
and
so perhaps there's a cycle 1, 2, 3, 4. Oh no.
yeah, but no. You see that if they are even, but the cycle is not. Yeah, maybe we should
It's 1, 3, 2,
again.
4.
Yeah. So the point is that the cycle 1, 2, 3, 4 is odd. 1, 2, 3, 4 is odd. So
It's
it is.
1, 3 to 4 then. Because alpha goes to alpha prime and alpha is 1,
It
alpha prime
doesn't
is
matter.
3. Well,
Doesn't matter.
oh yeah. Yeah, I understand what you want.
Because they are conjugated, so it doesn't matter. It's you can put any put them in arbitrary order, so they are all odd. Yeah. So so the conclusion is that and we know when a Galois group is contained in even permutations. Yeah. Yeah, so actually we can forget about this condition that m is negative. So the condition is different. So it is maybe we should just assume that it is not 0 and it is not a square. Yeah. So what is the condition?
Of the existence of such permutation?
Yes. So you see that what are the we have a subgroup. So this Galois group
Hmm.
is a subgroup of
Yes.
the symmetric group on 4 elements, and its order is 4. Its Galois group is 4. Yeah, so the options are that it is either cyclic or it is like this. So if it is like this, it is even. It consists of even permutations. Is that correct? Yeah, it is. I think so. Yeah. If yes, it is. So if it is, uh, yes, something. Yes. Yeah. So if it is like this, then it consists of even permutations. And do you remember the criterion? So it consists of even permutations if and only if the discriminant is a square. You see? So what we have to check here. So what is this discriminant? It is a square minus b square m times 8 b m square b square m. Yeah. So this is a square. We don't care about this square, and there remains this this element. And then the question is whether this element can be a square. Yeah. So can a square minus b square m be a square itself? Well, actually, you see that. So the answer is that, well, it's maybe a bit complicated. So do you know what is the Pell's equation? Do you know this? No? Well, maybe it's a little bit, maybe it would be a little bit easier. So yeah, if you don't know, then we come back to our assumption that m is negative, because so m is negative, because if m is positive, then so the point is that this equation has a solution for any y square. Has well, this equation has a rational solution. Sorry, wait. Rational non-trivial, yeah, because we don't want b to be 0, yeah, so has a rational solution, or if m is integer, is an integer, then it has a an integral solution. Solution. Well, with y 0. Sorry. If m is positive, yeah. So this is Pell's equation. Yeah. Now, what happens if m is negative? So, well, maybe we should not discuss this right now, but just maybe I can give you just an example. Sorry. Yeah.
Well, someone let us.
Sorry. Yeah. Okay. So. Rational integral solution. Yeah, maybe we should skip this and just let us look at. Well, maybe just a little example. So example. Actually, it has. Well, I say that it has a solution, but actually, it has many solutions. Many solutions. So example. You see that if you have one solution, then you can consider in a sense its powers. So you can, if you have one solution x naught and y naught, then you can consider x naught y naught square root of m and raise it to some power, and then you can transform this into the form xn plus yn square root of m, and this pair will be another solution. Yeah, and actually n can be an arbitrary integer here, so maybe negative, maybe positive, just any integer. So actually you have many solutions, and the claim is that if you look for integral solutions, then in a sense they come from a single solution like this. Well, maybe it's not a good notation, maybe I should put here 1. Make this consistent. Make this x1 equal to this x1 equal to this x1. Okay. Yeah. Now, what about negative? So if m is negative, then what? So we have we want, yeah. So we want this to solve the same equation. And y square is equal to 1. And well, so what do you think of this?
Maybe some differential. Well, no differential. We want
Sorry.
x square and y square.
Yeah. So
Mm, no.
well, maybe we should consider some case. Yeah. For instance, well, actually, it also has many solutions because you see, what is this? This is actually this is what is this? This is just something like it's an ellipse. Yeah. Well, I write this. Well, maybe it's not. It doesn't look like ellipse, but so this is 1, and this is 1 over square root of minus m. And what can you do is you can just you can draw all lines. You can draw all lines through this. So you see, you have a trivial solution. But using trivial solution, you can get many non-trivial solutions. Namely, you take lines passing through the trivial solution, but this slope coefficient of this line should be a rational number. So let me write this. The equation of this line is y is equal to lambda times x minus 1. Yeah. Yes. Y equals to x. Y is equal to lambda x minus 1, where lambda is a rational number. Yeah. And then sorry. Excuse me. Hello? Да-да, привет. Sorry. Yeah. So you see that what is written here. It is, you can rewrite this as m y square minus y square is equal to oh, maybe plus, yeah, maybe x minus 1 um, well, x square minus 1, yeah. So and when you replace y square by lambda times x minus 1, we get m lambda square times x minus 1 equal to x plus 1, yeah. And of course this linear equation has a rational solution, you see. So well, you can write that x is equal to what, to 1 plus m lambda square over m lambda square minus 1. Yeah, so you see that there are many solutions. Yeah, so that's how we get okay. All right.
And lambda here is.
It's an arbitrary rational number.
Mm-hmm.
So we get many solutions.
So
So
and wait. Okay, I understood.
but you see the difference here in Pell's equations. We were looking only for integral. So you see that actually you with m positive you can actually it doesn't matter. So here we only assume that m is non-zero. Yes. So yes, it's just non-zero. So and we get many solutions.
We
But
take the chord that. How do we
yeah,
put?
we just
We actually. How do we get this lambda?
we don't get it. We just take arbitrary. So we get. So the
Mm.
point is that that the solutions are pairs.
Okay, understood.
So m lambda square minus 1 and y is you can so you
Yeah,
have to
multiplied by lambda.
yeah
Lambda this minus lambda this minus one.
yeah so yes you subtract 1 and yeah you get something like this for all lambda for all rational numbers. So these are all rational solutions, and it's not important here which, so it may be not an ellipse but hyperbola. And so this is a hyperbola if m is positive, and well, you get many solutions here, but in Pell's equations means that you solve in in integers, and in case of positive m, you get infinitely many solutions.
And
But in
we
case of
assume that m is non-square.
yeah, but we have used this assumption earlier because otherwise some
Square root of m is in Q. Oh well, if m is negative, then it's fine.
yeah, the point is that if m is a square, um, oh, I'm sorry, here something wrong is, yeah, so it should be sorry, it's, yeah, it's correct, it's not here, maybe, yeah, it's yeah, so if m is square, then this polynomial is reducible, you see. So if m is square, then this is difference of two squares. So you can decompose it. So this polynomial is not reducible. And therefore, our extension is of degree 2 and not of degree, well, depends on what do you mean by, yeah, so it is of degree 2 and not of degree 4. Yeah, so that's the point. Okay. Yeah. What's wrong here? Can you hear me?
Yeah, once again, please. Where something must be wrong.
Yeah. This you see that if
this polynomial is
if m
irreducible.
is reducible, if m is a square,
Hmm.
then uh, then uh,
Then
um, then we don't. So we have an extension of degree 2
yeah,
and not of degree 4.
okay. Then well, we assume that m is negative. Then so m
Yeah,
is
that's actually yes.
automatically non-square.
Actually, we don't really. Yeah, we can come back to the assumption that it is not just a square, not a square, so it's not zero, and it's not a square. M is not a square.
While 0 is also a square, so we can.
Yeah. But I mean, I yeah.
Okay.
Okay. Yeah. So we use this assumption here, and then everything is. I think everything works.
Yeah.
So and we get what? Yeah. So when we use the fact that if our group is not cyclic, then it consists of even permutations, but it does not consist for certain choice of NB. For a certain non-trivial, yeah, non-zero choice of NB. And yeah, so that's the point. Yeah. So and actually, you see that there are many. And the point is that there are many. So maybe conclusion. Conclusion. There are many, well, infinitely many um, cyclic extensions containing square root of m. Okay. All right. Where is it? I cannot find. Sorry.
So, why is once again, please? Why is this extension of degree 4? Oh,
Uh,
no, not of degree 4. Its Galois group is Z4
um,
because
you see, first of all, it is well. First of all, it is of degree 4. Yeah,
yeah.
because we add a root of a polynomial of
So,
degree 4.
the discriminant is a square, then
It's not.
it is or
Oh,
it is not a square.
I'm sorry. I'm sorry. I'm talking nonsense. I'm talking nonsense because yes, I'm talking nonsense. Oh, I'm sorry. Excuse me. Mm, I was yes. Excuse me. Excuse me. I was yes. I had to say that it is. Uh, Yes, if it is, it consists of even permutation. Oh, yes, you're right. You're right. Yes, I'm talking nonsense because if the discriminant, we have constructed a pair for which the discriminant is a square. Yes, so
Yeah.
it's not what we want because if it is a square, then the permutations are even. So it gives us Z mod 2 square group. Yeah, I'm sorry.
Hmm.
I'm sorry.
So, okay, we actually know that there are A and B such that A square minus B square M is not a square.
Why?
Um, mm, for example, let's take oh well, 1 plus M can 1 plus M be a square?
Oh, in principle,
Oh,
yes.
well, in principle, yes. Then, all right. You see that we know let M be P over Q.
Yeah, so actually what we need be a non-square.
Mm-hmm.
A non-square. Sorry, what is our question? Our question is that, yeah, we want
So
a
if
non-square.
oh, you see, the Galois group consists of even permutation. It means that the discriminant is a square.
Yes.
So the discriminant is a square. So no, the discriminant is the discriminant's non-square part is 2a square minus b square m. Oh no, I'm talking nonsense. It's just a square minus b square m. All right then. Uh, well, um, all right then. Let's say that a square minus b square m equals. All right. I think. Okay, I'll just take some time to think about it.
Mhm.
Mm, so, all right. Let's try to solve the a square equals b square m plus one. Well, a square minus b square m equals 1, because in case it equals c square, we can replace a square with by a square over c square, and b square with b square over c square. Well, let's say a square
Okay.
minus b
Yeah,
square.
I'm sorry. I think I.
Короче, мы просто отнормируем по... Ну, потому что если оно не единица, а какой-то c квадрат.
Yeah. Okay. I think I know how to prove this.
Сейчас, так подождите, смотрите, если мы возьмем а квадрат минус b квадрат m равно единице,
Нет,
то тогда
if
у
it is.
нас при а равном единице b квадрат m точно не равно нулю, при b не равном нулю, и все хорошо. То есть пара 1 что-нибудь уже нам даст не квадрат.
Um, квадрат, да?
Ну, по идее. То есть,
О,
если мы а приравняем c, вот этому самому... проблема. Оно для конкретного c. Да. Ну давайте действительно попробуем единицы приравнять.
yeah,
Что
but
тут делать? Нет.
if it equals to one, then there is a solution,
М,
as I said. But we want a non-square. So we want a non-square, and hmm, it looks Yeah, so this is our determinant, yeah? Okay. Yeah, so, well, maybe we can consider uh, we may consider just some examples, yeah? For instance, we may assume that m is not a square, yeah? Because that m is square free. That we may assume that m is an integer. M is an integer, and it is square free. Uh, Next, if this means that if it is square free, then it is either either m is equal to -1 or so I mean that if it is square free, then either it is equal to -1 or its absolute value is not a square. Okay. Yeah. So
Seems fine.
okay. So this means that that in this case, so in case when m is not -1, then this equation has a solution. Because it has a trivial solution, namely 0, 1, and using trivial solution like this, we can construct a non-trivial. So construct non-trivial solutions. Infinitely many solutions. Okay. Sorry. Excuse me. Excuse me. Yes. So yes. So this is okay. Yeah. Do you agree that in this case we have a solution? Do you agree? So in this case that
Uh,
so the
Wait. In case modular m is not a square.
yeah.
Well,
Sorry.
the absolute
Yes.
absolute m is not square. Why is there a solution? Because we found it earlier.
Because yes, because you see that this is not a square in any case, yeah. Because if it is negative, then it is not a square. If it is positive, then it is not square by this condition. Okay.
Once
So
again,
and
uh,
so this is not a square, not a
yeah,
square.
m is not a
And
square.
minus m
Minus
is not a
my
square under this condition.
yes.
And this equation has a solution, namely 0, 1.
Mm-hmm.
And then we draw the same picture and get a non-trivial solution. Non-trivial where both coordinates are non-zero. So non-trivial non-trivial solutions. Non-trivial solutions. You see that you just played the same game. You take a point here and draw the lines passing through this trivial solution under rational slope. You see this one. But there you have to change. You just draw instead you change the roles of x and y. You write x is equal to lambda y minus 1. Yeah, and then you substitute in this, so you get lambda square y minus y minus 1 plus is equal to m times y plus 1. Yeah. So this is the system. Yeah. So you solve this equation and find the x. Yeah, for all rational lambda. Okay, and yeah. So but the case left is what happens if m is minus 1. So then, well, then of course you then it's not a problem because you can take just b square. You have to solve. You have to show that this can be non-square. Yeah, but it's not a problem because you just take 1 and 1. Yeah, then a square plus b square is 2, which is not a square. Yeah, and that's it. Okay.
Again, so we get the pair 1 1 gives us.
Well, gives us a non-square. Yeah. So well, maybe well, maybe it's. I have to stop at this point, but maybe you can try to check all the details. Yeah, because we were a little bit sloppy somewhere. So essentially, yeah. So essentially, what have we done? We just look at parity, yeah, parity of permutations, and the parity of permutations are yeah, they are controlled by the discriminant. Yeah, and so our task is just to make sure that our discriminant is not a square. So if we want our group to be outside of alternating subgroup. Okay. All right.
So we get pair 1 1. Then we get a square plus b square equals 1, and y
Equals to.
equals 2, and why is it?
Yeah. Okay.
We take
And therefore the discriminant. So you see that what is our discriminant? Our discriminant is
a square
this
minus b square m.
minus b square m. Yeah, and therefore it is not a square.
Yeah.
It is not a
Wait,
square
why is it not a square in case a square plus b square equals 2?
because 2 is not a square.
And so we here we assume that m is minus 1.
Yes.
Okay.
But if it is not minus 1, then we can.
How do we get non-trivial solutions?
In which case?
In case m is non-square.
The same way. So you draw the picture. You draw the picture. Well, let me write here x square minus y square. You draw a picture like this. Take the trivial solution here. But well, it will be here actually. It will be,
Mm-hmm.
you see that the point is 0,
Yeah.
1. And then draw all lines of this type
Mm,
for all rational lambda.
mm-hmm.
So they pass through this point, and they have other intersection point with this ellipse or hyperbola.
Okay.
Okay.
Understood. Thanks.
Yeah. Okay. Great. All right. So then we have decided that we meet on mm,
It seems that
on Wednesdays. Yeah. On
well,
Wednesdays for
we have a seminar on Wednesday, so the
yeah.
idea is to make it double.
Okay. All right.
All right then.
All right. So
So I'll inform everyone else that we've decided that
okay.
we
All
have a
right.
double seminar.
Yeah. So then see you on Wednesday.
All right.
Yeah. Bye.